Hello, am I audible? Hello, am I audible? Is my voice clear? Hello. So, hello everyone, I am Himanshu, and in the last class we actually looked few problems related to summation of forces and movements. So basically we solved couple of problems which actually involves the summation of forces which we represented by R and the summation of movement. So let's say we saw a body where n number of forces are acting from any random direction, and the resultant force, we were interested in calculating the resultant force, and for some problem we have already given the information about the resultant force, and we have been asked to calculate any unknown forces. So in this tutorial we will look problems in which equilibrium is involved. So basically we will solve problems uh, which follows the equilibrium conditions. So we will see exactly what it means. And before moving to the equilibrium, we will solve a couple of problems related to the movements, because last class we have solved only two problems related to the movements. We saw that the movement, if we write in a scalar form, then it can be defined as the force multiplied by perpendicular distance. And if I write in a vector form, then it is position vector cross product with the force. And then we discussed about how to calculate the perpendicular distance, and then we discussed that how to we actually discussed about the sign convention for the movements. So I believe we should solve few more problems related to the movements, because it's a very important concept and it will be used in an overall static course, and it is also used extensively in the trusses problem. So before going to the equilibrium problems, we will solve few couple of problems related to the movements, and then we will briefly. Yeah, this session will be recorded. Yeah. So then we will briefly discuss about what is uh, mean by the equilibrium condition, how we solve the problems in which the bodies or the systems are in the equilibrium conditions, follows the equilibrium conditions. So let's begin with the question. So in this note, still I have three or four problems left, I guess. So I will solve only two problems here. Rest of the problems you can solve by yourself. So the concept will be the same here. Basically, you have to use this equation of motion, which is given by the summation of force and summation of moments, to calculate the unknown quantities. So let's solve this question. So in this question, we have given uh, the sum of the movements about point A due to the forces and couples acting on the bar is 0. What is so the first part is, what is the magnitude of the couple C, and determine the sum of movements about point B due to the forces and couple acting on the bar. So basically we need to find the movement at point C, and we have given the condition that movement at point A is 0. So this is the condition we have given, that movement at point A is 0, and we need to calculate movement at point C. So as we discussed in the previous class, that in order to find the movement at any point, we need to fix the point. So if we need to calculate the movement at point C, we need to fix some point somewhere in this diagram. So let's say we fix point A, because we already know the information about point A, right? We already know this information, that movement at this point is 0. So if I try to calculate the movement, or basically if I use the equation of motion for the equation for the movement, which says that it is actually the summation of force multiplied by displacement. It's a scalar equation, and this is 0 at A. So I can use this equation. I can actually collect all the forces and their perpendicular distance, and then I can actually calculate movement and the unknown forces. So here we need to calculate the movement. So this equation I can more specifically write Ft plus m, because this is the movement and this is also a movement. So here I am actually, this summation of m can be can represent the movement due to a couple like this, and this F into d is actually the movement due to the point forces, which in the diagram is shown in the blue color, like here. So as we discussed in the last class, so 2 points, there are 2 points which we need to be note about. First thing is the perpendicular distance. So if I consider point A, what are the forces which are actually creating the movement? So we can see that this 4 kilonewton and 5 kilonewton is not creating any movement, because the movement is given by force multiplied by perpendicular distance, and the perpendicular distance is 0 for 4 kilonewton and 5 kilonewton case. The perpendicular distance from this force to point A is 0, which means these two forces will not create any movement at point A. Then this 2 kilonewton force will create a movement because it has this perpendicular distance, right? So the first, among the 2 points, the first point is to identify the perpendicular distance, and for this 2 kilonewton the perpendicular distance is 5 meter. For 3 kilonewton the perpendicular distance from point A is this 5 plus 3, which is 8 meters. Then we can also look this force, 4 kilonewton force. So here also this force will create a movement about point A, because the perpendicular distance to force 4 kilonewton to point A will be this one, which is actually 3 meter. So the first point is to identify the perpendicular distance for all the forces, and that we have identified for these 3 forces. So just to revise, there are 2 points which we need to ensure about while calculating the movement. The first is to define the perpendicular distance for all the forces, and second point, to define the sign convention. So just for the newcomers who join now, I will repeat. So here in this question we need to calculate the movement C, and we have given the condition that the movement at point A is 0. So we select a point A here, and then we have to calculate the movement at point A. We already know it's 0, but then we will get from the equation, the movement equation, we can actually get the details about various forces and various unknown movement, and this is the quantity at C we need to find. So we need to identify which forces is actually responsible for creating the movement about point A. And we can see that this 5 kilonewton and 4 kilonewton force is not creating any movement because the perpendicular distance is 0 from point A to these forces. But 2 kilonewton force here, it has this perpendicular distance which is 5 meter, and it will create a movement. And same for 3 kilonewton force, it has the perpendicular distance which is 8 meter, and it will create a movement about point A. And this 4 kilonewton force will also have a movement about point A because it has a perpendicular distance of 3 meter. So we identify perpendicular distances for all the forces. Now the second case is to define the sign convention. So if I consider anti-clockwise as positive and clockwise as negative, which means that this this 20 kilonewton meter movement has a positive sign, so I will write ma equals plus 20. Now these two forces will not create any movement, so we will not be bothered about this. Then there will be a movement due to this force, 2 kilonewton force, and you can see it is pointing downward direction. So the rotation about point O will go like this, right? So it is creating a clockwise movement which is negative. So it is minus 2 kilonewton force multiplied by perpendicular distance which is 5 meter. Now similarly, for 3 kilonewton force, the direction is downward, and the rotation about point A will be clockwise, which means it has a negative movement about point O. So it's 3 kilonewton multiplied by 8 meter. Then for 4 kilonewton, this is the direction from left to right, and about point O, it is again rotates in the clockwise direction, which means it will be minus 4 multiplied by 3, which is perpendicular distance, and the overall movement at point A is 0. So this overall movement will be 0. And sorry, there is a couple also at C. There is a couple. There is a movement which is acting that we need to find, and we can see from the diagram it is acting in the counterclockwise direction. So it will be plus m at point C. And this is the unknown quantity in our equation. So when we simplify it, we will get 0 equals 20, 10, 24, 12 plus m at C. So when we solve this, we will get movement at point C, which is 26 kilonewton meter. So we will get this positive 26 kilonewton meter, which means that the magnitude of this movement is 26 and the direction is in, as we mention here, it's a counterclockwise direction. So this is the movement at point C. Now in the second part of the question, we need to find the movement at point B. So let's try to calculate the movement at point B here. And we already know the movement at C. So we will also consider the movement at point C. Right, so again, We will repeat the exercise. So thing, the first task is to identify the perpendicular distances from all the forces, and second task is to determine the sign convention for each movement. So let's see which forces is creating the movement at point B. So earlier at point A, these two forces were not responsible for exhibiting any movement because they had the perpendicular distance equals to 0. But now we can see that this 4 kilonewton force has a perpendicular distance of this, which is 3 meter from point B, and 5 kilonewton force has a perpendicular distance of this, which is 5 meter. So both this force is creating or inducing the movement at point B. Again, this forces now doesn't have any perpendicular distance to B. Sorry. So this will not create any movement, and this force also doesn't have any perpendicular distance to D. So this force will not create a movement at point B, and this force 3 kilonewton is having the perpendicular distance of 3 meter. So we have identified the forces which will induce the movement at point B. Now we will follow the sign convention. So we follow the same. Counterclockwise we will consider as positive, and clockwise we will consider negative. So now let's consider 4 kilonewton force, this one. So you can see it will rotate in the clockwise direction around point B, right? So the movement due to this force will be negative. So it will be minus 4 kilonewton multiplied by perpendicular distance, which is 3 meter here. Then the rotation of this 5 kilonewton around point B will be again clockwise direction. So again it's negative, which is 5 kilonewton multiplied by 5 meter. Then this will not create any movement, and this force will not create any movement. So this 3 kilonewton force will create a movement because it has a non-zero perpendicular distance, and it will rotate in a counterclockwise sense around point B. So it is 3 kilonewton multiplied by 3 meter. And then we need to consider these movements which I have shown in this figure at point A and point B. Which is here 20 kilonewton meter, and we found at C which was 26 kilonewton meter, and the direction is it's positive 20, and this is also positive 26 because it's in counterclockwise direction. So this will give us the movement at point B. So it is minus 12 minus 25 minus 9 plus 20 plus 26. So when you calculate this, you will get MB equals to 0, which means there's no the magnitude of the movement at point B is 0. There's no movement at point B. So just to recap here, we have been solving question in which we need in the first part we need to calculate the moment at point C. So we actually considered point A because we have given the information that at point A it's 0, the moment is 0. So we use the summation of moment equation to calculate the moment at point C. Of course, we uh, fulfill the two tasks that we need to take care of. First, to find out the perpendicular distances for all the forces, and second, to ensure the sign convention. Then in the second part, we have been asked to calculate the moment at point P. So it's a straightforward problem here. We just consider the moment due to all the forces and due to couples as well, and then we calculate the movement at point P, which come out to be a 0. So any doubt in this problem? If not, then we can move to the next question. So you can see in all of the question until now we have been using the same principle, that the summation of force is given by R and the summation of movement is, let's say, some M, and we have been using this two coupled equation to calculate the unknown force and unknown movement. So this is the last question based on this. Then we will move to equilibrium. Hello. Junaid, do you have any doubt? Okay, sure. Can you just turn off your mic? Okay, it's fine. So let's solve the problem. So we have given the vector sum of the forces acting on the beam is 0 and the sum of movement about A is 0. What are the forces AX, AY and B? What is the sum of the movement about B? So again we have given the condition that the movement at point A, which is this, is 0, and we need to calculate the forces AY, AX and at B, and we need to calculate the movement at point B also. So again using the same equation here, equation 1, and let's say this is my equation 2. The summation of forces, let's say in the x direction, will be given by Ax plus component of this force, which is 400 cos 30, and it is being given that the vector sum of forces acting on the beam is 0, which means it should be equal to 0. The summation of force Fx should be equal to 0. So this is my equation 1. And in equation 2, I have to sum all the forces in the vertical direction. So it is Ay plus the component of this force, which is 400 sine 30 plus B equals to 0. So this is my equation 2. So in the previous problem that we have solved until now, we have been using these two equations to calculate the unknown force. But as you can see, you have two equations here and you have three unknowns. So Ax is unknown, Ay is unknown and B is unknown. So you need a third equation here. So until now we have been using the force, summation of force equation and summation of moment equation separately to calculate the unknowns, but now we will use three equations, and the third equation definitely will come from the summation of movements. But for summation of movement, we need to fix the point from which we are taking the movement actually. So let's say we fix point A because the movement at point A is 0. So we can actually use this equation. So the movement at point A is 0, which is given in the question. So we actually can sum the movement at point A and equate it to 0. So it will be ma, and the moment will caused by force B because it has perpendicular distance which is 500 millimeter. And let me draw the component of 400 Newton force. So this is X component, let's say, and this is my Y component. And this is 400 sine 30. So this force will have a movement because it has a perpendicular distance of 220 millimeter, but 400 sine 30 will not create any movement about point A because it doesn't have perpendicular distance. So the force we should consider is 400 cos 30 and B. And for the sign convention, let me fix counterclockwise as positive and clockwise as negative. So B will rotate in counterclockwise direction about point A. So this the movement due to force B will be positive, and this 400 cos 30 will rotate in clockwise direction about point A. So the movement due to this 400 cos 30 will be negative. So it is positive B multiplied by 0.5 meter minus 400 cos 30 and its perpendicular distance, which is 220 millimeter. So I will consider 0.22 meter equals to 0 because in the equation it is given movement at point A is 0, which is, so you can also see that these are the three equations, and these equations actually follows the equilibrium conditions that we will shortly discuss. So this is my equation 3. So now we have to, it is all about algebraic calculations. So we have three equations and we have three unknowns. So from third equation we can actually calculate the value of B. So it is 76.2. So B will be 152.42 Newton meter. Sorry, this is force. Sorry, so this is Newton. 152.42 Newton. So this is the value force at B we got. So we have already got B. So now this have only two unknown, AX and AY. So we can use this equation 1 and 2 together to find. So we actually use equation 1 alone to find the AX. AX is AX is actually plus 400 cos 30, so it will be minus 400 cos 30. So it will come out minus 346.41 Newton. And from equation 2 we can calculate AY because we already know B. (400 sine 30), so it will be 200 plus B, and B is 152.42. So when you solve this, you will get minus 352 Newton, point 4 Newton. So this is your AY and this is your AX, and this is the unknown force at point B. So we have calculated all the unknown forces which have been asked in the question AY, AX and B, and for that we have used three equations because there were three unknowns AX, AY and B, so we used three equations. The first two equations come from the summation of force and the third equation comes at summation of movement at point A. Now the second part is what is the movement at point B. So basically now we need to calculate the movement at this point. And we know AY, we know AX. So now as usual, we need to identify the force which induce the movement at point B. For that we need a perpendicular distance, non-zero perpendicular distance. So AX has non-zero perpendicular distance to B, which is this 260 millimeter. AY don't have any perpendicular distance, so AY will not induce any movement at point B. AX will, because it has 260. It has perpendicular distance 260 millimeter from point B. Now 400 cos 30 force will have a perpendicular distance which is 220 plus 260 millimeter, and this force 200 Newton, which is the vertical component of this force 400, is having perpendicular distance which is this 500 millimeter. So both this force will induce the movement, AX will induce the movement and AY will not have any movement. So we have to consider the movements due to the force AX 400 cos 30 and 200 Newton. And for the sign convention, you can visualize. So the 400 cos 30 will rotate about clockwise direction about point B. So it's a negative movement. It will have a negative movement according to this sign convention. 200 is directing to downward direction, so it will rotate in a counterclockwise direction. So this is positive. It will induce a positive movement. AY will rotate like this. Sorry, let me draw in the different color. So AY will rotate like this in a clockwise sense, which means it induces a negative movement around point B. So AY and 400 cos 30 will have a negative movement and 200 will have a positive movement. So let me solve here only. So movement at point B will be plus 200 multiplied by 500 millimeter, which is 0.5 meter. Then 400 cos 30 multiplied by this perpendicular distance, which is 220 plus 260, which is 480 millimeter, which so it is negative movement. 400 cos 30 Newton multiplied by 0.48 meter. And then there is AX, which we calculate minus 346.41. And it has a perpendicular distance of 260 millimeter, which is 0.26 meter. So this is the summation of movement at point B. So when you calculate it, you will get movement at point B is minus 156.334 Newton meter. So basically it is a clockwise movement at point B. So actually we say that AY will not create a movement, but AY also has a perpendicular distance actually. So this is the perpendicular distance for AY. It's like similar to the 200 Newton force, because both actually are parallel to each other, just in a different opposite direction. So we should also consider AY force, and the sign is it is rotating like in a clockwise direction about point A. So it will be minus AY, which is 352 multiplied by perpendicular distance, which is 500 millimeter, 0.5. So this should be plus, because it has a negative movement, but the force is also a negative. So minus minus will become plus. So this should be plus. So it will be 100 minus 166.27 plus 90, and this should become plus also. So 176 . So it will come out to be positive 199.8 Newton meter. It is actually a counterclockwise movement at point B. So just to recap here, we have been given two parts in this problem to solve. In the first part, we need to calculate the unknown forces, and to do that, we actually use three equations. So the two equations will come from summation of forces from equation 1, and the third equation come from the summation of movement, because we have been given three unknowns to find AY, AX and B. In the second part, we need to calculate the movement at point B. So we identify the force which create the movement, induce the movement at point B, and then using the sign convention, we actually directly calculate the movement. So any doubt in this problem? So if not, then we can move to equilibrium. So now we are going to solve problem based on the equilibrium, which actually follows the equilibrium condition. So this concept is very important in the static, because most of the problems that you will going to solve in trusses and in beams will follow this condition. So in equilibrium, the resultant force is 0 and the resultant movement is 0. So until now we have been using the similar equation where the resultant force was not 0 and the resultant movement was not 0. But in equilibrium condition, both are 0. So these are the required condition and equation to satisfy the equilibrium in the problem. So these are the three set of equation that we are going to solve. So the summation of the force and movement now we consider will always going to 0 to fulfill the equilibrium condition. But what is exactly equilibrium condition? So for example, let's say you have a body here and it is experiencing some force R. It's a resultant force which came due to the summation of all the forces. Now, if this body can accelerate only when this R is non-zero. So from the Newton's second law, your R is equals to ma. So if your force R, resultant force R is non-zero, which means this body will have acceleration. It will move and it will also accelerate. But let's say if your R is 0, then only two conditions are possible on here. The first condition is body is at in a static, uh, there is no motion in the body, so which means the velocity of this body is 0 because there is no motion of this body. The second condition is if the body is already moving with some velocity, let's say v, it will always keep moving with this velocity because the acceleration is 0, because this force r is 0. So basically if r is 0, the acceleration will also get 0. So if body is moving with velocity v, it will always keep moving with this velocity because acceleration is just the change of velocity in time. So if my acceleration is 0, which means my change in the velocity is also 0, which means if I write the change as v2 minus v1 equals to 0, then it will give me v2 equals v1, which means the velocity at later time equals to the velocity at the previous time v1. So equilibrium condition maintained when the body does not move, the body is not in the motion, or body moves but with a uniform velocity. Basically when the acceleration in the body is 0. So you can see in many question it has been given that the body is moving with the uniform velocity, then you've been asked to calculate the forces. So in that case you should always use these equilibrium equations. If body is moving with some acceleration or with some angular acceleration or something, then we need to use this equation that we have seen in the previous classes, and we will actually again see about these equations in the later tutorial when we talk about kinetics and kinematics. So until now our objective is to solve the problem where the equilibrium condition maintains. So basically what happens, this body is actually feel force R due to which it accelerates. But if the resultant force is 0, the body will not accelerate. But there can be a different different forces which are actually act on the body. And this random different kind of forces can be captured by this summation of forces, right? Which means that, so basically you need to understand that if you exert any force on the body, it doesn't mean the equilibrium condition vanishes. The resultant of this force should vanishes, not this component of this force, not each of this force. So body can experience forces from several directions, from several sources, but the resultant of all of these forces should be 0 in order to satisfy this equilibrium condition. So let's say you have forces on this body due to different cases to Fn. Now there can be non-zero F1, F2, F3, F4 or F5, but the summation of all these forces should be 0 in order to satisfy the equilibrium condition. And same goes with the summation of movements. So when we say that the force is 0 which causes the acceleration is 0, I actually mean the total force or the resultant force is 0, not each of these individual forces. In fact, these individual forces, we are interested in these individual forces to calculate, that we will see in our problem. Now in order to calculate all these internal or individual forces, we actually need to make the free body diagram. So for the movement case, we actually very clear about the two situations, first to calculate the perpendicular distance and then to follow the sign convention. In these kinds of problem, our first objective is always to draw the free body diagram. So for example, let's say you have a system in which you have given multiple members here. So you can see there are three bodies which are interconnected to each other, and in order to find the forces in each of the body, your first step should be to isolate each body. Let's say you need to find forces in this body here, then you should isolate this part of the body from the remaining system. So you just isolate it, you draw all the forces which are acting on this body. So it could be due to the body force, it could be due to the surface force, or it could be due to the reaction forces. So just identify all the forces which are acting on this body and then use this equation. And from this equation, you can actually calculate the number of unknown forces, F1, F2 or F3, whichever is required. Then once you are done with this body, then isolate this part of the body and repeat the exercise. Again use this set of this equation, equilibrium equation, on this body by isolating it after isolating it, and then repeat this exercise for this one. So this is the traditional method to solve the equilibrium problems. First make the isolate the body, then made a free body diagram by considering all the forces in the free body diagram, and then use the equilibrium equations here, which is given by 1 and 2, to find the unknown forces and unknown movements, and then repeat the exercise for all other members of the system. So let's briefly look at the number of different forces that can act on the system or the body. So some of these forces we already discussed in the previous lecture in terms of body forces and surface forces very briefly. But there can be another types of there can be different classification of forces also, like reaction forces, which is very prevalent in trusses and beams problem. So let's say you have a body here, a spherical body which is moving in some random direction. Now let's say this body contact with a wall. When it contact with the wall will exert a reaction, equal and opposite reaction force R. If I assume that my wall is smooth, then it will exert a reaction force R. Just a minute. So for a smooth wall, when I ignore the friction, it the body will experience a reaction force R from the wall, which is in the opposite direction but equal in magnitude. But if my wall is non-smooth, then there will be a components of R in the vertical and horizontal direction. Let's say Fx and Fy. So while making the free body diagram, you need to consider these reaction forces also. Now there can be other reaction forces from pin joint. So this can be your pin joint, which you might have seen in trusses problem. So what happens here? So here this member actually can rotate, but it cannot translate in any direction. It cannot translate in x direction, it cannot translate in y direction, but it can rotate either in clockwise direction or in anti-clockwise direction. So its motion is constrained in translation, which means that there is a reaction forces which is acting in x and y direction. but it can rotate either in anti-clockwise direction or in clockwise direction. Then there is a built-in support. Let's say you have a cantilever beam, it is actually fixed in the wall. So you can see again, this cannot move in x direction, this cannot move in y direction. So again there will be a reaction forces Rx, Ry, but also it cannot rotate. So there will be a reaction movement also. So in earlier case here, it can rotate. So there was not a reaction movement in the pin joint, but in the built-in support, this bar cannot rotate, which means its rotational motion is constant. Due to this, there will be a result reactive movement at the wall, which will occur. So along with the reactive forces, there will be a reactive movement also occur. So when you draw the free body diagram, in such case, you need to consider all of these reactive forces and reactive movements. Similarly, about the body force that we have discussed, for the gravity, you actually consider force as mg, and for the spring forces, you actually consider the spring force as kx. K is the spring constant that usually given in the question. So using all of this knowledge, like using all kinds of different body forces, surface forces, smooth reaction forces, non-smooth reaction forces, and the reaction forces in the pin joint as well as in the support, we can actually make the free body diagram. But first you need to isolate that part, then make the free body diagram by using all of these forces, and then we can use this equation of equilibrium to calculate the unknown force and movements. So this is the basic concept in the equilibrium that we will see. So let's solve the first question. So here, if the in the question we have, if the 1.5 meter long cord AB can withstand a maximum force of 3500 Newton, determine the force in cord BC and the distance Y so that 200 kg crate can be supported. So the weight of this is 200 kg. So there will be a, so sorry, the mass of this crate is 200 kg. So there will be a weight or the gravitational force which is acting here. And we have given the force on AB, which is 3500 Newton. And we need to find the force at chord BC. So the first step is to draw the free body diagram. So this is my point B. So there is a weight 200 kg multiplied by 9.81 meter per second, second to the power minus 2. So this is the weight or the gravity force. Then there will be a force which is acting here. So this is 3500 Newton. Which is acting in some theta. So we don't know the theta here. So now and this is force BC. Right, so we gather all the forces in our diagram, so we know the information of all the forces here, and there are two unknown from this free body diagram. The first unknown that we need to calculate is F force at BC, and the second unknown is theta, because this theta is required to calculate force at BC, because we need to consider the component of this force in the x and y direction, right? So now we will use the, yeah, hello. Hello, Pratish. I think you raised the hand. Is there any question, Pratish? Okay. So we will be using the equilibrium equations, which is summation of force in both direction is 0 and summation of moment should be 0. This can be split into fx equals 0 and the summation of fy equals 0. And this is a sign which I usually follow for the vector notation, and this is for the scalar. So if I consider summation of force in the vertical direction is equal to 0, then I need to consider the vertical component of this force and this gravity, because I don't need to consider this force because it's in horizontal direction. So actually I can calculate theta. So it will be 3500 minus 200 multiplied by 9.81 equals to 0, and this should be sine theta here. 3500 sine theta is the vertical component of the force. So it will be, sorry, sine theta equals 200 multiplied by 9.81 divided by 3500. So it will be around 0.56. So when you calculate, your theta will be around 34 degree. So this is our theta. So now from this equation you actually got theta. So now if you follow this equation, let's see if we get force at BC. So when we do the summation of force in the x direction, in the horizontal direction, we need to consider the force in the chord BC, the component of 3500. That's it. Which means we can actually get the force. So it is 3500 cos 34 plus FBC equals to 0. So just to be note, I am equating it to 0 because it's in the equilibrium condition. So when you solve this, you will get force at BC, which is minus 2.9 kilonewton, which means that our assumed direction of this force is wrong. It should be pointed like this, because it came out to be negative. So this is the force at BC, and this is the theta that we have find out. And now we need to calculate the distance y so that 200 kg crate can be supported. So the length of this coat is given, which is 1.5 meter. So this we can actually easily calculate, because to calculate this distance y, we actually need theta, and that we have already calculated here. So this can be calculated by sine theta equals y by 1.5. So y will be 1.5 sine 34. So y will be 0.838 meter. So just to recap here we have been given the rod, various chord here. The chord AB experiences a force of 3500 Newton, and we need to calculate the force at chord BC and the distance y. So we actually used the summation of force equation and equated to 0 because it's an equilibrium condition, because it is given in the equation that the 200 kg crate should be supported. So following this equation, we actually calculate theta first because it requires to calculate force at chord BC. So we actually calculate theta from summation of force in the horizontal direction and equate it to 0. Then once we get the theta from this equation, we actually use summation of force in the vertical direction to calculate the unknown force at chord BC. And then from simple trigonometric relation, it is very easy to calculate distance y. So any doubt in this? If not, then let's solve a similar problem. So it's a very similar problem here. So the towing pad end AB is subjected to the force of 50 kN exerted by the tugboat. Determine the force in each of the bridles BC and BD if the ship is moving forward with a constant velocity. So as you can see in the question that it is given that the ship is moving forward with a constant velocity. The constant velocity ensures that the whole system is in equilibrium because there is no overall or resultant force acting on the system. I should say no total force which is acting on the system, which ensures the acceleration of this ship is 0, and due to this the velocity of this ship is constant, and therefore we can use the equilibrium equations. So let us first write down that Fx, force in the x direction, is 0, force in the vertical direction is 0, and the summation of movement is 0. So these are the equations that we need to use here again. And we need to calculate the force in the chord BC and BD. So first, let's make the free body diagram. That is the first step. Let's say this is my A. It is experiencing 50 kilonewton. Let's say this is BD, and this is point B. This is BD and this is BC. And this is at the angle 20 and this is at 30. And these are the two unknown forces that we need to calculate. So let's use this equation one by one and let's see what we got. So if I use first equation 1 here, in which I do the summation of force in the horizontal direction and equate it to 0, then I don't need to consider this force, 50 kilonewton force. I just need to consider component of FBD and FBC in the horizontal direction, and which we can find as FBD minus sine 20 plus FBC, and this is sine 30, and this summation should be 0 to follow the equilibrium condition, right? Here I consider minus sign because you can see if I make the coordinate system, this is my positive x, this is my negative x, this is positive y, and this is negative y. and you can see it is actually moving in this direction, which is in the negative x direction. So this force is negative, and this force is actually moving in the positive x axis. So this is, and therefore I consider this force as a positive. So you can see this is the one equation, but we have two unknowns, FBD and FBC. These are the two unknowns. So we cannot solve by using alone this equation. So now we need to consider equation 2 also. And let's see if we can solve. So if I do the summation of force in the y direction, so I can consider this force minus 50 kilonewton because it's in minus y direction. Then the component of this force in the y direction, and we can see both are in positive y direction. So it will be plus FBD cos 20 plus FBC cos 30 equals to 0 to ensure the equilibrium condition. This is equation 4 and this is equation 5. So now you can see two unknowns and two equations, which means we can solve this equation. So from equation 4 we have FBC sine 30 equals FBD sine 20. Now it's all algebraic exercise, mathematical exercise. So I can write force at BC as force at BD sine 20 divided by sine 30. So I can write force BC as like this. You can also write FBD in left side and FBC in the right side. It doesn't matter. I choose to write F like this, like FBC in the left hand side direction. Then I substitute this expression of FBC in equation 2. Minus 50 plus FBD cos 20 plus, and instead here I will replace this FBC by this expression. So it is FBD sine 20 divided by sine 30 multiplied by cos 30 equals to 0. So now you can see you have only one unknown here, which you can easily found. So this will be 0.939 FBD, and this term will be 0.59 FBD equals 0. So it will come out to be minus 1.531 FBD. So FBD will be 32.658 kilonewton. Now you can substitute this FBD either here or in equation 5 or in equation 4, in any of this equation, to calculate the force in FBC. So let's say I choose equation 4 where I substituted the expression value of FBD. So it is minus 32.65 sine 20 plus FBC sine 30 is 0.50. So this come from equation 4, this one. So this will become 11.166 equals to minus FBC. So this FBC will be 22.33 kilonewton. So again, it was pretty much a straightforward problem because the only thing you need to remember is to use the equilibrium equation. But before that, first make a clean, nice free body diagram. So identify all the forces in the free body diagram. So in this case, it was a 50 kilonewton, and the forces, unknown forces in the chord BD and CB. Once you identify the forces, then you use the equilibrium equations one by one to calculate the unknown force. So rest all of this are just the mathematical exercise. So I need out. So if not, then we can move to the next problem. So you can see it's a similar problem again. So here you need to determine the magnitude and direction theta of the equilibrium force AB exerted along the link AB by the tractive apparatus as shown. The suspended mass is 10 kilogram, which means this is 10 kilogram. This has the mass of 10 kg. I need to determine the force at AB. So again, it's a similar problem where you can, in free body diagram, when you make the free body diagram, you need to identify this as the force, this is the force, and this is the unknown force that you need here. And theta also you need to calculate here. So you make the free body diagram and use the equilibrium equations that we have been doing since a couple of problems to find the unknown theta and FBD. See? So in the first problem, in fact, we actually calculate the unknown theta and the unknown force here using the similar principle. So this was the theta that we have considered or calculated, and then we actually calculated force at BC. So it's the same or the similar problem that you can try out. So this PDF I will upload in the drive, and you can try this problem by yourself. If you cannot able to solve by any chance, then we can discuss this problem in the next tutorial. Meanwhile, we can move ahead to the problem number 4. So again, it is kind of a similar problem, except the fact that in one of the chord we have been given the spring force. So instead of allotting the random force in this chord in the free body diagram, we need to consider the expression of spring force, which is given in terms of kx, and k is the spring stiffness, which is 800 Newton per meter. So in this problem, the spring has a stiffness of 800 Newton per meter and an unstretched length of 200 millimeter. So it has the unstretched length of 200 millimeter here, and the remaining is, let's say we have delta S. Determine the force in cables BC and BD when the spring is held in the position shown. So when you stretch this spring, then what is the force experienced by the chord CB and DB that we need to find. So again, a similar problem, but there's a difference here that in the chord AB, the force is due to the spring force. And to calculate the spring force, we can use the expression for the spring force, which is given in terms of K. and it should be delta x. So this should be a delta x here, which is, and the delta x is the unstretched, sorry, the final position of the spring minus unstretched length. So basically, let's consider this is the spring you had. It has the unstretched length of 200 millimeter. You have not stretched the spring, but then let's say you stretch the spring, and this is the new length, and this is given as 500 millimeter, which means the difference here is delta x, and this delta x is zero point 0.5 minus zero point 0.2. So here I'm writing in meters, so it will be zero point 0.3 meters or 300 millimeters, and the spring force is equal to force in the chord AB, which will be K delta x. So force in the chord AB will become 800 Newton per meter divided by zero point 0.3 meter. So this is 240 Newton, which means the force in this chord AB is 240 Newton. So once we get the force here, once we get the force in the chord AB, which is 240 Newton, now we can make the free body diagram and we can repeat the exercise that we have been doing since the couple of problems. So this is the force at BC, and this is my force in BD, and we have just calculated the force due to spring, which is equal to force in the chord AB, and this is actually equal to 240 Newton. So if I, this is positive x, positive y, negative y, and from the diagram you can see it actually split equally. So this is 90, and it splits equally, which means this should be 45, this should be 45, just by inspection here. So we made a first we actually calculate the force in the chord AB by using the spring force relation. For that we first calculate delta x, then we use the spring force relation to calculate the force in the chord AB. Once we got the force in the AB, then we made a free body diagram where we consider the force due to AB, force in the AB due to spring, which is 240 Newton, and other two unknown forces. We show all the forces in the free body diagram here. Then once you make the free body diagram here, now you can use your equilibrium equations. So as you might have noticed that until now we have been using this two equation only to calculate the unknown force, but we have not used this equation until now because we have been not required this equation until now, because in earlier two equation there were only two unknowns. So this two equation would be enough to calculate those two unknowns. No, it can be a 45-degree because you can see it is actually distributed in a symmetric way, right? So if this is 90, this is 90, this is 90, this is also 90. If this is 45, then this should be the remaining 45. It's like 90 minus 45 here. So this angle should be 45, and this angle also should be 45. And you can actually see, Just a minute, I can see this. Yeah. Yeah, this is what I'm thinking. Yeah. So then it could be just a second. Hmm. So the above is 45 because this is 400 and this is 400, but here it is 300. So yeah, it should not be a 45 here. And here I can use the ratio. So this is 3, this is 4, so it become 5. Okay. So okay, so I can use this ratio to calculate the angle. So this is not the 45 here. 5. Alright. So this will be 45. Yeah. Yeah, thanks for the info. So now with the given edited free body diagram, we can use this equilibrium equations. So let's say if I do the summation of the force in the x direction, then I will have here 240 Newton, which is pointing in the x direction, plus FBC cos 45. Sorry, the direction here should be towards minus x-axis, because you can see the spring is stretched, so there will be opposite, there will be a force toward point A, not toward points B, so this should be a negative. And this force FBD will have the horizontal component, which is 4 by 5 here by triangle law, positive here. And this should be equates to 0. So 2 unknown, so we need another equation, so this will be summation of force equates to 0 in the vertical direction. And here we need to consider only these two forces, so we have FBC sine 45 in the positive, and this should be in the negative y, so this will be minus FBD, and from this triangular law we can have 3 by 5 equals to 0. So this we actually discussed in the previous class. Like our first question was, if we have given the angle and the triangles ratio, then how to calculate the component of the force. So these are the two equations we have and two unknowns. So we can use the second equation to write the relation between FBC and FBD. So there will be some expression. So my FBC can write as FBD point 6 divided by sine 45. So this will become 0.848 FBD. So this is the expression of FBC here. So if I put this expression here in equation 1, so I will have minus 240 plus, instead of this I will write this, because FBC equals to 0.848 FBD. So I can write whole equation 1 in terms of FBD. So here I will have 240 minus 240 plus 0.599 FBD plus 0.8 FBD. So it is 240 equals minus 1.4 FBD. It will give me FBD equals 240 minus 1.4. So FBD will be 171 prox Newton. So this is my FBD. Now I can substitute FBD, value of FBD here, or you can substitute it anywhere, 1, 2 or this equation. So your force in FBC will be 0.848 multiplied by 171. So it will come out as 145.37 Newton. So this is the unknown force you need. So just to recap here, it was a similar question. The only difference is we have given the spring here in the chord AB. So we first need to evaluate the spring force in the chord AB, and that is actually equal to the force AB. So for that we first calculate the unstretched length delta x. Then using the spring force relation we actually calculate FAB, which is equals to spring force. Then after that we made a free body diagram, and using the equilibrium equations we calculate the other unknown forces, which was FBC and FBD. Any doubt in this one? So let's move to the next one. So in this problem we have the beam has a fixed support at A and is loaded by the two forces and a couple. Draw the free body diagram of the beam and apply the equilibrium to determine the reaction at A. So as we discussed previously, that for the fixed support, since this beam cannot translate in x direction, so let's say this is my x direction and this is my y direction. Since this beam cannot translate in x direction or y direction, there will be a normal reaction or the reaction forces. Let's say AX and AY. Now for the fixed support, this beam cannot rotate as well, which means there will be a reactive movement also which will act, right? So this we have discussed in the beginning, that for the pin joint there the translation motion is constant. It cannot move in x direction, it cannot move in the y direction, so there will be a reactive forces, but it can rotate. The rotation is possible for the pin joint, so there will be no reactive movement. But for the fixed support, the rotation is also constant, so there will be a reactive movement along with the reactive forces. Right? Then in order to make the free body diagram, we need to consider other forces, which are 4 kilonewton, this is 2 kilonewton at 60 degrees, and there is a movement or a couple which is acting here, which is 6 kilonewton meter, and we need to find this we need to find this AX and AY, right? So until now we have been using only two equations, two equilibrium equation, which was force in the horizontal direction is 0, force in the vertical direction is 0, and in this question we may use the third equilibrium equation, which is the summation of moment at a given point is 0. So let's see if we can use third equation. So let's use first equation where the summation of force in the horizontal direction is 0. So for that, the horizontal forces are Ax, and then the component of this force, which is 2 cos 60. Its cos 60 is 1, so it is Ax plus 1 equals 0, and it will give us Ax equals minus 1 kilonewton. So from this equation alone we can able to get the value of Ax. Now let's use Ay. Sorry, let's use the summation of force in the y direction and we equate it to 0. So we have Ay plus 4 plus the component of this, which is 2 sine 60, and the summation of it should be equals to 0. So when you solve this, you will get Ay equals to 5.732 kilonewton. Right? So again, just by solving the equilibrium equation in the y direction, summation of force in the y direction, we actually got the answer. So we have calculated Ax and Ay. Now let's calculate this unknown reactive movement. So this is point A, and if I take the movement at point A due to all the forces, so first we need to determine the perpendicular distances. So for 4 kilonewton it will be this, which is 1 meter plus 1.5 meter, and here you have a two component of force in the x and y direction. So x direction, x component of 2 kilonewton, which is 1 kilonewton here, you can see here, does not induce any movement at point A because it does not have any perpendicular distance. But y component here, y component force have the perpendicular distance, and it is actually the whole length of this beam, which is 1 plus 3 meter, 4 meter actually. And then we need to consider the movement at point A and the movement at point, some random point here, which is 6 kilonewton meter. And we can have the sign convention as clockwise positive now and counterclockwise negative. So here I change the sign convention just to show you that you need to fix the sign convention as per your convenience. But then once you fix the sign convention, you need to follow this for the entire problem. So in this problem, I fix the sign convention where the clockwise is positive. You can also fix otherwise where the clockwise movement is negative and vice versa, vice versa. So the movement at point A is ma. So this is ma. It's a positive because it's in the clockwise. And the movement due to 4 kilonewton force will rotate like this about point A, which is anti-clockwise. And same goes with this force, again anti-clockwise. So the moment due to force 4 kilonewton and the component, vertical component of 2 kilonewton is a negative. So here it is minus 6, sorry 4. Yeah, I mean we also need to consider this movement. So and it is in counterclockwise, so it is, yeah, it is already a minus 6. Then due to the force 4 kilonewton, it is minus 4 multiplied by 2.5. And there will be a moment due to the vertical component of this, and it will be minus 2 multiplied by 4, and this all should be equals to 0 for equilibrium. So your MA will be minus 6 minus 10 minus 8 equals to 0. And you can see it come out to be 24 kilonewton meter. So this is when you use the third equilibrium equation, summation of movement at any point equates to 0. So using all these three equations of equilibrium in this question, you can actually calculate unknown reactive forces and reactive movements here. But let's say you have given here a pin joint and not a fixed support. Then when you make the free body diagram for the pin joint here, for the given instant, this will be your free body diagram. There will be a reaction force Rx and Ry, but then there will be no movement because this pin joint allows that it can rotate in any direction, clockwise or anti-clockwise direction. So this beam now can rotate due to pin joint, and due to this rotation, its rotational motion is not constant. Therefore, you don't have this reaction movement at point A. So I said that at a given instant, this will be your free body diagram. I said this as a given instant because this beam can rotate, and from the gravity, this beam actually rotate in this direction, and this will be your final position of the beam, right? After the rotation, Rx, and this will be Ry. So if you consider the pin joint, for this instant you don't need to consider the reactive movement force at point A. You just need to calculate Rx and Ry. But for the fixed support, since the rotation is constant, then you need to consider the movement here at point A, because this movement is constraining the rotation. So any doubt in this problem? So we can solve next problem here. So the first part is draw the free body diagram of the beam, and the second part is determine the reactions at the support. So again, in order to determine the reaction at the support, you need to see what kind of support you have given the problem. So earlier you have been given the fixed support. So you had the two reaction force Rx and Ry and a reaction movement Ma in the fixed support, because the rotational motion and translation motion were constant. Now here you have given two different kind of support. So here you have roller joint, and here you have pin joint. So about the fixed support and pin joint we already have discussed. Now we can discuss about the roller joint also. So in roller joint, the translation motion in one direction is not constant. For example, here in this case, this bar can actually move in the y direction, either upside or downside. So this bar actually can move in the vertical direction here. It can move to upside or downside, which means there is no reaction force in the y direction. But this bar cannot move in x direction. It cannot move in x direction, which means its motion is constant in x direction, and there will be a reaction movement Rx. So here there will be a reaction movement Rx due to a constant motion in the horizontal direction. But then there is no reaction force in the vertical direction because it can move in the vertical direction. So in the roller joint, one direction is constant. Here I am talking about translation motion. Sorry. And also it can move, it can rotate. It can rotate like a pin joint. So again there is no reactive movement. There is no reactive movement. There is no reaction force in the vertical direction. There is only a reaction force in the horizontal direction. So this was all about the roller joint. In the pin joint, the translation motion is constant in both direction, x and y, which means it cannot move in x, it cannot move in y. So there will be two reaction forces. Let's say by and bx. So there are two reaction forces, but it can rotate. It can rotate, so there will be no movement at reactive movement at b. So let me summarize. In roller joint, so this is pin joint. So here in this question, in the roller joint, it can move in the y direction, it can rotate. So you have only reaction force Rx. Or let me call this Ax. But in pin joint, it can only rotate, but it cannot translate in any direction. So you have both reaction forces. Now it cannot have Ay, it cannot have rotational reaction forces because it can move in those direction. Similarly, it cannot have it cannot have the reactive movement at point B. Right? Now with this information, we can actually made a free body diagram. So this is point A. This is point B. So here you have Ax, a reaction force. Here you have By, and here you have Bx. Then this is the external force, 40 kilo Newton. And we need to determine the reaction forces Ax, By, Bx. This is 6 meter, 8 meter, this is 12 meter. And the unknowns are Ax, Bx, By. So you can see there are three unknowns. So we should use three equilibrium equation, which is Fx equals to 0, Fy equates to 0, and movement at a given point equates to 0. So this equation should be imply on the free body diagram. And from the given knowledge of roller joint and pin joint, we actually figure out what are the reaction forces are acting, or if there is a reaction moment which is acting or not. In earlier question it was acting because for the fixed support there is a reaction movement at point A, but for roller and pin joint there is no reaction movement. So based on this information we actually made a free body diagram, and now our objective is to calculate this unknown force. So when we do the summation of force in the x direction, we have ax plus bx equals to 0. Question 1, sorry. If we do the summation of force in the y direction, we have 40 plus py equals to 0. It will give you py equals minus 40 kilonewton. So you already now got by, but you don't know ax and bx. So you have to use the third equation, which implies summation of movement should be equals to 0. And here I choose to take movement at point A, which means for 40 kilonewton I have already a perpendicular distance 8 meter to point A, and for by my perpendicular distance is 12 meter from point A. There is no movement due to ax, and no, there is a movement. So to, for bx my perpendicular distance is 6 meter. So this three force will induce the movement at point A. So we figured out the perpendicular distance. Now we need to figure out the sign convention. So let's say my counterclockwise positive, clockwise is negative, which means this 40 kilonewton rotate about point A in the counterclockwise direction. So this have positive movement around point A. My bx will rotate in a counterclockwise direction about point A. It induces a negative movement about point A, and by will rotate again in the counterclockwise direction, which means by will induce positive movement. So it's pretty easy to see the signs of each movement induced by each of these forces about point A. So we just write. So first write 40 movement due to this 40, which is 40 plus 8 plus by movement due to by, which is minus 40 multiplied by 12, then due to bx sorry multiplied by 6 equals to 0. So it will give you minus 160 bx 6. So bx is 26.6 minus kilonewton. So the direction of bx we considered is wrong. Bx should be in this direction. And we found the value of bx, which is 26.6 kilonewton. And we found the value of by, which is minus 40. Now we need to find ax. And from equation 1, we know that ax equals to minus bx. So if bx is minus 26.6, then my ax is 26.6, positive value. So here you can see that we actually calculate all the unknown reaction forces by equilibrium equations. So just to revise, we have been given a problem with two different kinds of joints and we need to find the reaction forces. First we need to draw the free body diagram and then we need to find the reaction forces. So if it is not given in the question, like in the part A it is given draw the free body diagram. Even if it is not given, you should always first draw the free body diagram here. And to do that, you need to figure out the reaction forces in the joint. And it depends on the type of joint. So we have seen three type of joint: roller, pin, and fixed. So in roller joint, it the body or the part of the body can move in only one direction and it is constant in other direction. So if it can move in x direction, sorry, if it cannot move in the x direction, then you have only reaction force in the x direction because it is constant in x direction. It cannot move in the x direction, so you have only reaction force Rx. And in the y direction it can move, so you cannot have Ry, so Ry is 0, and it can also rotate, so Ma is 0. In pin, it cannot move in x and y direction, both in x and y direction, so you have Rx, you have Ry. But it can rotate, which means the reaction movement is 0. In the fixed joint that we saw in the previous problem here, it cannot move in x and y direction and also it cannot rotate, which means you have to calculate Rx, Ry and also reaction movement. So when you do make the free body diagram, you need to consider which joint you need to notice which joint you are actually have given. And based on this information, you actually draw the free body diagram. So you can see here you have only one reaction force Ax in the roller joint, and in the pin joint at B you have two reaction forces, which is Bx and By. So once you draw the free body diagram, identify all the reaction forces, all the forces in the free body diagram, you use the equilibrium equations to calculate the unknown force. So any doubt in this problem? So if not, then we can meet next week. So next week we will start problem intricacies, which is actually extension what we did today. So in the trusses as well, we need to use the principle of equilibrium, and we will use different method to find the unknown forces. So basically, we have to follow the principle of equilibrium in trusses. It's just that in trusses we can use two methods, method of sections and method of joints, to calculate the unknown forces in the member. So method of joints is the same method that we have been using until now. It just we need to use the equilibrium equations at each member to calculate the unknown force. So this is what you actually do in method of joints. But in method of section, you actually divide the truss into two parts and then you use these same equilibrium equations. So basically it is just the extension of what we did today. So next week we will start with trusses. Thanks.